Hi everyone. Now we are at eigenvalues and eigenvectors, lecture number 8. So one review on lecture number 7. Problem number 1. Lecture number 7, problem number 1. We are supposed to diagonalize the matrix. Problem number 1. There, characteristic polynomial. I got this one, which is determinant of a minus lambda I. This one I got as some lambda plus 1 into lambda minus 7. This I got, and directly eigenvalues have written lambda 1 is equal to 1 have written and lambda 2 is equal to 7 have written. So by mistake I have written 1, but it is not 1, it is minus 1. Make a note of it. Okay, it is minus 1. And the corresponding what diagonal matrix is what? So diagonal matrix is nothing but the eigenvalues will sit on the principal diagonal. So simply minus 1 0 0 7, or you can write 7, you can write here 0 and 0 minus 1, you can write like this also, no problem. Just eigenvalue should be on the diagonal. That's it. Make a note of it. And characteristic polynomial, and one more. Determinant of a minus lambda I is equal to 0. This is characteristic equation. Okay, characteristic equation. And determinant of a minus lambda I, just determinant. This one is characteristic polynomial. If it is equal to 0, that is equation. Otherwise, it is polynomial. Okay. Yes. Next one. So diagonalizing a square matrix A by a special matrix P. So is another concept. Theorem number 3. Continuation to lecture number 7. Two theorems I have done in lecture number 7. Now theorem number 3 in lecture number 8. Continuation. If a square matrix A of order n has n linearly independent eigenvectors x1 to xn corresponding to the eigenvalues lambda 1 to lambda n respectively, then a matrix P can be found such that P inverse into A into P is a diagonal matrix. So what is P? We can find a matrix P such that P inverse into A into P. What is A? A is a old matrix. For this matrix, these are the n eigenvalues and these are the n eigenvectors. Okay. So pre-multiplication with P inverse and post-multiplication with P. Then this togetherly, this become diagonal matrix. Okay. Now let us go to the proof for this. Yeah. Proof. Given that, listen carefully. Given that lambda 1, lambda 2 up to so on, lambda n are eigenvalues of the matrix A, and what is given x1 x2 up to so on xn are linearly independent vectors. So what is meant by linearly independent vectors? So simply I will tell you roughly. Look at, see for example, let us take a matrix. Okay, the first row is 1 2 1, the second row is 2 4 2 for example, and the last row is 1 5 7. Let's assume. So this is 3 by 3 matrix, square matrix, and this is row 1, row 2 and row 3. Okay, look at the second row is obtaining by multiplying first row with 2. Multiply this row with 2, what will you get? So this is R1, and this is R2 second row, and this is R3. Now how I am getting R2? Simply multiply second row with first row with 2. Look at 2, 4, 2. So indirectly this row is depending on first row. From first row you are obtaining this. Then I can say that these two are dependent vectors. Okay, they are depending. But look at 157, this vector does not depend upon any of the row. The last vector 157 does not depend upon the any of the these two vectors. Therefore, this is called independent vector. This alone is an independent vector, but these two are dependent vectors. Like that. See, for example, 1 0 0, okay, and 0 1 0 and 0 0 1. Look at this one. Or you can look at column wise also. Look at the first column. The first column is 1 0 0, second column 0 1 0, third column is 0 0 1. Look at column wise you look at. Second column can you obtain by first column and third column? Can you obtain? No, we cannot obtain. By adding these two, you cannot get this. If I add C1 and C3, C1 plus C3, then what I will get 1 0 1 I will get. But this vector I don't get. I won't get. If I subtract, I will not get second vector, second column vector. So therefore, this is similarly each and every column will not get by using any other column vectors. Therefore these three vectors are linearly independent vectors. Independent vectors, they are not depending on any other vectors. That is called independent. Independent means not depending. So each three vectors are here, three column vectors are not depending upon the any other vectors. Therefore these three are linearly independent vectors. Similarly, one more example. Look at this. 1 3 0 2 1 9, okay, and 3 4 9, for example. Look at this. See, this vector cannot be obtained by this vector. This vector is not obtaining by this vector. Look at, by multiplication or division, whatever. And what about this vector? If I club these two, R1 and R2, if I do R1 plus R2, what I will get? R3 only. Look at, R3 only I will get. Club these two. So therefore I can say that these three are dependent vectors, linearly dependent vectors. Dependent, they're not independent. Okay, they're depending. So once they are depending, indirectly what will happens is, see, if look at from this example only, particularly these three vectors are linearly dependent vectors. They are not independent, they are dependent vectors. Okay, because this vector, third vector, is obtaining by using first two vectors. Therefore these are dependent vectors. Okay, now in this third last row 3 4 9, we will make it as 0. How to make it as 0? Simply by using row operations. Okay, by using row operations we will make this one is 0. So therefore this entire row becomes 0. Then if I find the determinant of this matrix, we will get 0. Det of that matrix is 0. For example, this matrix is A, then definitely det A becomes 0 if you are having linearly dependent vectors. Similarly, look at this one. These are independent vectors. Okay, if you find the determinant of this matrix, determinant of B is not equal to 0, because none of the row is vanish. If none of the row is vanishing, indirectly det is not equal to 0. Okay, if any of the row is completely vanishing, indirectly det is 0. So that is a sign of linearly dependent vectors. Okay, and look at this, here also this row become completely 0. How? Simply you modify R2 as, how to modify R2 minus 2 times R1. If I do this one, this middle row completely becomes 0. Then one row becoming completely 0. Therefore these vectors are linearly dependent vectors. So if I find the determinant of this matrix, first matrix, you will get 0. So if you are having linearly dependent vectors, the det is 0. If you are having linearly independent vectors, the determinant is not equal to 0. Remember this concept, and this concept I will apply here in this proof. Okay, now look at what is given to us. N eigenvalues are given and n eigenvectors, independent vectors, are given to us respectively. Okay, so these are the n vectors. Okay, linearly independent vectors respectively. So therefore what I can write is a into x1 is equal to lambda 1 x1. Can I write? Because x1 is an eigenvector corresponding to the eigenvalue lambda 1. Similarly, assume this is 1. Similarly, a x2 is equals to lambda 2 x2. Okay, yes or no? So ax2 is equal to lambda 2 x2. Similarly, ax3 is equals to lambda 3 x3. So assume this is number 2, second equation, this is third equation. Okay, and up to so on. So clearly I can write axn is equals to lambda n xn. This is number nth equation up to so on. Okay, so now I'm going to generate an equation. So before that I want to define one matrix. Okay, the matrix is, so let P be a matrix, P be a matrix. What kind of matrix I'm taking? This matrix I'm taking as having x1, x2 up to so on xn as columns. Okay, these vectors I am taking as a columns of this matrix. So now, so therefore the matrix P is, indirectly the matrix P is, so the matrix P indirectly, which is the first column is x1, okay, second column is x2, okay, and third column is x3. So up to so on, last column is xn. So this is my matrix P. I'm defining like that. Okay, why I am defining like this we'll understand soon. So next step, now let us define, or let us find the value of a into p. I want to calculate a into p. What happens? Okay, the given matrix A, which is of order n by n, and what is p here? The matrix P is having eigenvectors as column vectors, right? x1, x2 up to so on xn. So this is n columns. So this is matrix P. Okay, this is matrix P into, I'm doing into a into p. So p is nothing but this matrix. Okay, and what is the order of this matrix? It is n by n only, right? Because x1 having n components, column vector it is. It is eigenvector, right? Eigenvectors is a column vector. How many components will be there? N components, because a is of order n by n. A is of order n by n. Therefore, with respect to lambda 1, the eigenvector x1 is of order n by 1. N by 1. N rows 1 column. So similarly, x2 order n by 1. N rows 1 column. Similarly, xn order n by 1. So overall, n by n matrix. So this is n by n matrix. Which one? P matrix. A is also n by n. Therefore, matrix multiplication is possible. So next step, what I want to do is, now let us multiply column wise. So a into x1, right? So matrix A multiplying with first column x1. Next, matrix A multiplying with second column x2. So up to so on, and matrix A multiplying with nth column. Okay, next one. So look at equation number 1 to n. What is A into x1? A into x1 is nothing but lambda 1 x1. Yes or no? Similarly, A into x2 is lambda 2 x2. Okay, next up to so on, A into xn, lambda n xn. Okay, this one, since by using, since by using equation number 1 to n, by using equation number 1 to n, all these equations I am using. Okay, so then next step, now I want to modify this step. How I modifying is, in this I want to take common as x1 out next x2 is out, up to so on, xn is out into, observe carefully. See, if I multiply these two matrices, I should get this matrix again. Okay, such matrix I need to choose here. So that matrix will be, look at. So lambda 1, 0, 0, up to so on, 0. What I'm doing, look at, if you multiply this column, this row with this column, what happens? X1 into lambda 1, sorry, lambda 1 x1. Look at lambda 1 x1. Next x2 into 0, 0. Okay. Next x3 into 0, 0. Up to so on xn into 0, 0. So only first component become present here, lambda 1 x1. Okay. Next, how to get lambda 2 x2? Same thing, but here we need to keep lambda 2. And all other entries are zeros. Okay. Similarly, so up to so on, here what we need to write? Up to so on, 0, 0, 0. So last one is lambda n. So indirectly only diagonal entries I am keeping eigenvalues, and remaining all other entries are zeros. Okay, so if I multiply this matrix with this matrix, what I will get? The first entry should become lambda 1 x1, second entry should become lambda 2 x2, up to so on. The last entry become lambda n xn. Am I getting? Check once. So this entire row with this column, what will get? So that will be, that should be written in the first entry, right? Next, this entire row with this second column, that should be written with here second entry. Yes or no? So therefore, am I getting or not? You check once. So first I'm multiplying with this row, with this column. Am I getting? Look at x1 into lambda 1 plus x2 into 0 plus up to so on xn into 0. Indirectly I'm getting only lambda 1 into x1. Look at this first entry. Similarly, second entry, lambda 2 x2. Am I getting? Check once again. This entire row with second column. Multiply now. Here x1 into 0, 0 plus x2 into lambda 2 plus x3 into 0 plus up to so on xn into 0. So only lambda 2 x2 is getting like this. So similarly we are getting this, the resultant matrix, right? So therefore this entire matrix you can split like this. Okay, so then what is this? So let us look at this matrix. First one is nothing but what? uh, so this one is nothing but our p, right? What we defined just now, p into, now there's a new matrix which is diagonal matrix, in which the eigenvals are sitting on the diagonal, principal diagonal. So call this matrix as some d. I am naming it as d. Okay, so now what I got, a into p. So let me write here. So a into p is equals to p into d I got. Okay, where where what is d? D is a diagonal matrix which is nothing but lambda 1, 0, 0, up to so on 0. And similarly the second row, 0 and 0, lambda 2 here, and all other entries are zeros, and up to so on. So like this, up to so on, the last entry will be lambda n, like this. Okay, so this is a diagonal matrix. So this is d. Okay, or simply you can write this one as, all these are just notations. This matrix also can write d as like this, d is equal to sum. So since it is a diagonal matrix, you can write the entries like this, lambda 1 comma lambda 2 comma up to so on comma lambda n. So this is a representation of a diagonal matrix. So it means lambda 1 will be the first entry in the diagonal, lambda 2 will be the second entry in the diagonal, up to so on lambda n will be the nth entry in the diagonal. You can represent like this also, diagonal matrix. Fine. So now I got this result, a into p is equals to p into d. Now what is the use of this? Remember, we are diagonalizing the matrix A, right? So that's what we are getting the diagonal matrix out. Okay, now from this what I want to do is, look at here, from this result, assume this is number some first Roman, because already 1 to n equations I have taken. So from this equation, from this equation, from here, from this equation, pre-multiply 1 with P inverse. Does P inverse exist? Does P inverse exist? Yes. Why? Because what is matrix P? Matrix P is nothing but x1 to xn. x1 is the first column, x2 is the second column, up to so on, xn is the nth column. But what kind of column vectors these are? They are linearly independent column vectors. So if I do the determinant of P, I will get not equal to 0. Okay. Since determinant of P is not equal to 0, therefore determinant of P, okay, determinant of P is not equal to 0, therefore P inverse exists. Okay, P inverse exists. So therefore clearly I can write this one. I can pre-multiply both sides with exist. So since P inverse exists, now this step is makes sense, right? So then if you do that, what you will get? Pre-multiply with that. Ah. So I got AP is equals to PD I got. Now I am pre-multiplying both sides with P. Pre-multiplying. So P inverse AP is equals to P inverse P into D. So this is nothing but P inverse AP is equals to P inverse into P. How much? Identity matrix into diagonal matrix. So now identity matrix into diagonal matrix is diagonal matrix itself. You take any matrix, multiply with identity matrix, you will get D only. That matrix itself. Okay. And this is P inverse AP. So indirectly what you got, but what is P here? Diagonal matrix. So indirectly you are diagonalizing the given matrix. What is our goal? We have to diagonalize the matrix A. If it is a diagonalizable matrix, then what is it similar to? It is similar to this one, right? D. What is D? D is nothing but in the principal diagonal, all eigenvalues will sit. Okay. So therefore, here, so therefore, this I can write as finally. So therefore, P inverse AP is equals to D. But what is D? D is nothing but D1, oh, sorry, lambda 1, right? Lambda 1, lambda 1, lambda 2, up to so on, lambda n. All the diagonal ends are sitting on the principal diagonal. That's it. Our proof is over. What is our theorem? Our theorem is a matrix P can be found such that P inverse into AP is a diagonal matrix. Look at P inverse into AP is a diagonal matrix. So hence the proof. Hence the proof. So here what you have to understand is, if the matrix A is given to us, first you find all the eigenvalues. Okay, you will get all the eigenvalues. Then corresponding eigenvectors we calculate. Okay. If all the eigenvectors are linearly independent eigenvectors, then clearly matrix P is nothing but first column is first eigenvector with respect to lambda 1. In this second column is nothing but second eigenvector with respect to lambda 2. So up to so on like that we can construct what is P. So once P is a matrix which is having linearly independent eigenvectors, then P inverse exists automatically. Then P inverse and P we can calculate. Okay. Then multiply P inverse, multiply A with pre-multiply A with P inverse and post multiply A with P, so that this matrix become diagonal matrix. So this is another way of proving that the matrix A is diagonalizable or not. Okay. If such P is not existing, for example, A is not diagonalizable, indirectly P having linearly dependent vectors. So once P having linearly dependent vectors, then A is not diagonalizable. In the problems I will show you how it is not diagonalizable, how it is diagonalizable. Okay, so this is about the proof. And here we need to make a note number one. If x1, x2 up to so on xn are not linearly independent, then the result is not true. Not true, not true. That is indirectly which result? The matrix P, if the eigenvectors are not linearly independent case, okay? If they are not linearly independent, then the matrix P is does not exist. Does not exist. Because I want only linearly independent eigenvectors, right? So if these are not linearly independent, then such a matrix P does not exist. So therefore, P inverse into AP is not diagonalizable. Therefore, P inverse into A into P is not diagonalizable. So that is the result. Okay. The main thing is the all the vectors should be linearly independent. Okay. So that we should take care. Otherwise, it is not diagonalizable. Clear? And if you want more information, so in the above result, the matrix here, the matrix P we obtain, right? The matrix P is said to be modal matrix. Modal matrix. Modal matrix. And the matrix D is said to be spectral matrix. So this is modal matrix. Okay, this is modal matrix. And D is said to be, and D is spectral matrix. Spectral matrix. These are having some special names, nothing else. Okay, spectral matrix and modal matrix. Okay, next one. Obtaining powers of a matrix by diagonalization technique. So here how to find the powers of a diagonalizable matrix. For example, A is a diagonalizable matrix. How to find A power 4, A power 8, A power 10, A power 2000 like that. Okay. In general, we can do A into A square I can do by calculations. A into A square A cube I can calculate like that. But if it is A power 20, the calculation becomes more lengthy, right? So to avoid such complicatedness, now we are going to use this result. The result is, look at, already just now we got AP is equal to PD or P inverse into AP is equal to some D. So from that result I am going to obtain here. Okay. So let A be a diagonalizable matrix. So therefore there exists a P matrix P such that, what kind of matrix? Such that P inverse into the given matrix A into P should be equivalent to diagonal matrix. Okay, and take this result as 1. Now what I am doing is take that result repeatedly. So D is equal to, so therefore D is equals to P inverse into A into P, right? Okay. Then next, how to compute D square? D square is nothing but D into D, right? D into D is nothing but P inverse into AP, P inverse into A into P. This one you have to multiply with again P inverse into A into P, like this. Okay. This is nothing but what? Which is nothing but P inverse A. Okay. Again P into P inverse. Look at this one. So first I want to multiply these two. Okay. P inverse into P, A into P. And then what I will get? P into P inverse is identity matrix. So P inverse into A into identity matrix into A into P. Okay. Now this become P inverse which is A into identity matrix is A only, right? So A and into A into P. Okay. And this will be P inverse into A square. Okay. Let me write here. So this is equivalent to P inverse into A square into P. So what I got now, the result is D square is equals to P inverse A square P I got. Look at here. So therefore to find the A square here, look at P inverse and P are not becoming squares, right? Only D and A only changing. Look at this is a fundamental result. Okay. From here what is happening? If I do D square, only A square is becoming. P inverse and P does not changing. Let us do one more. Okay. So this is one. The next one is, let us take D cube. What happens? Then we can observe the result. So D cube is equal to is nothing but D square into T. Okay. And this is nothing but what is D square? Just now we computed P inverse into A square into P. Okay. P inverse into A square into P. This is D square. Okay. Into what is D? P inverse A P. This is D. Right. So in the next step this become P inverse A square into P and P inverse A into P. Now P into P inverse become identity matrix. So this become now P inverse, okay, into A square, right? P into P inverse is identity matrix. Identity matrix into A into P. Now what you will get? So this is implies P inverse, directly I am writing A square into identity matrix is A square only, A square into A cube. So P inverse into A cube into P. Look at, I started with D cube. I ended with P inverse into A cube into P. So similarly in this, so finally what I will get is, so therefore the observation, so therefore, so similarly Similarly, we can write as, what we can write? So d power n is nothing but p inverse, okay, p inverse into a power n into p inverse into a power n into p. So this is the general uh, formula where n belongs to natural number set. N belongs to natural number set. Okay. So in this, I want, see, generally A is given to us. A is given to us, and we supposed to verify whether A is a diagonalizable or not. If it is diagonalizable, then we supposed to compute some A power 8 or A power 10 like that. Then separate A power n from here. How to separate? Look at A power n. The pre-coefficient is P inverse. Okay. Then multiply with P so that P into P inverse become identity matrix. Okay. And look at again A power n. Look at the post coefficient. Post coefficient is P. Again, if you multiply with P inverse, post multiply with P inverse, then P into P inverse become identity. So the two operations I want to do here. So what I will do, first pre-multiply, first pre-multiply so pre-multiply with P both sides, then what will you get? P into d power n, and this become P into P inverse, okay, a power n, a power n into P. Okay, now this become what? This becomes P into P inverse is identity matrix. Identity matrix into A power n is just A power n only. I'm writing. So A power n into P. So here what I'm getting? P into D power n. P into D power n. So in the similar way, now I want to retrieve what is A power n. Then I don't want this P, right? RHS side. Then post multiply with P inverse both sides. Okay. Let us write post multiply with P inverse both sides. Now look at post multiply with P inverse both sides. Then what will you get here? Post, so P into D power n P inverse. This is post multiplication, which is equivalent to A power n into what happens? A power n into P inverse becomes identity matrix. Directly I'm writing A power n. So finally, A power n is nothing but P into D power n into P inverse. Now you are having all the eigenvalues. First, for example, matrix A is given to us. Then we need to compute eigenvalues, right? So that eigenvalues are nothing but diagonal entries of D. Okay, then D power n I can calculate easily. Simply, what is A square? If I do square, here also square become, right? D square is nothing but square of each and every eigenvalue. Okay, and P is with you and P inverse is with you. Simply you have to multiply these three matrices so that you will get A power n. If n is equal to 100, simply D power 100 into P inverse, like this. So D power 100, how to get D power 100? Simply lambda 1 power 100, lambda 2 power 100, lambda 3 power 100 up to so on lambda n power 100, which are in the diagonal, and pre-multiplication with P and post multiplication with P inverse. That's it. You will get A power n. So now the result is here. So A power n is nothing but P into D power n into P inverse. So this result I will use for finding powers of the given matrix. Look at obtaining powers of, look at the heading, obtaining powers of a matrix by diagonalization technique. So here we are obtaining powers of a matrix by diagonalization technique. This is a diagonalization technique only. Okay. Here what is D power n? D power n is nothing but all the diagonal entries which are sitting in the diagonal, main diagonal. What is that? First entry will be lambda 1 power n and all the entries are zeros. In the second row, first entry will be 0, second entry lambda 2 power n and remaining entries are zeros. And third row, first two entries are zeros. Third entry lambda 3 power n and remaining entries are zeros, like that. So that is a matrix D power n. And with this I will stop. I will continue in the next class with some problems. Okay.